Welcome to this technical session on top gas recycling with carbon recycling methanation. In this presentation, we will explore an innovative approach to enhance the sustainability of blast furnace iron making. We'll start by understanding the collection and the processing of top gas, moving into the methanation process, and highlights its key features and benefit. So these are the three aspects that we are going to discuss. We will also address the challenges, look at looking at the global projects, and we will also try to dive into chemistry and energy calculation that underpin this technology. Our goal is to provide actionable insights for improving furnace efficiency and reducing carbon emission. So let's begin. Moving to our first topic, let us discuss the collection of the top gas, which is supposed to be the foundation stone of this activity. The gas, also known as blast furnace gas or BFG, is collected at the top of the furnace. It contains a mix of carbon monoxide, carbon dioxide, and other impurities that need to be managed. To ensure its usability, the gas is passed through a scrubber and other cleaning system to remove these impurities. This clean gas becomes a foundation for the recycling process. We will explore next, setting the stage for more sustainable operations. We focus on the separation of now CO and CO2, which is supposed to be one of the most important activity in this project. After cleaning, the top gas undergo a critical step where carbon monoxide and carbon dioxide are separated. This process is essential because it allows us to isolate the gases for further utilization. The separated CO and CO2 are key inputs for the methanation reaction, which we will cover in the following slide. This separation ensures we will maximize the efficiency of the recycling loop. So now coming to the heart of the process, the synthetic methane along with separated CO and hydrogen is injected back into the blast furnace through the tuyer, and here hydrogen acts as a effective reducing agent, converting iron oxide like Fe2O3 or Fe3O4 into metallic iron while minimizing CO2 emission. The reduction reaction is Fe2O3 plus 3s2 2Fe plus 3s2O, which produces water vapor instead of CO2, significantly lowering carbon emission. Any excess CO2 generated, perhaps from combustion, is captured using CCS technologies for recycling or storage. Additionally, the process captures unused heat from the furnace and the top gas system, boosting energy efficiency. This integrated approach marks a shift towards greener iron making. Now let's look at the key feature of carbon recycling and methanation projects, particularly those in Japan. First, CCUS integration allows capture CO2 from the blast furnace to be reused, stored or converted into valuable product. Second, hydrogen utilization leverages water electrolysis powered by renewable energy, linking the process to green hydrogen production. Third, the generated methane serves as a carbon neutral energy source suitable for reinjection or other industrial uses. Finally, this aligns with carbon neutrality goal, supporting decarbonization and sustainability. These features highlight the technology's potential to transform steel production. Now coming to the benefits of the top gas recycling and methanation. The methanation process reduces net CO2 emission by recycling CO2 into methane, which can be reinjected into blast furnace. It also cuts coke consumption by replacing it with hydrogen and methane, reducing reliance on fossil fuel. The exothermic nature of methanation provides additional heat, improving energy efficiency. Moreover, it fosters a circular carbon economy by capturing, utilizing, and converting CO2 into useful product like methane, lowering the overall carbon footprint of steel production. These advantages make it a compelling strategy for modern iron making. Now it's a time to look into the challenges and considerations. However, the high initial costs are a significant hurdle as equipment for gas separation, hydrogen production, and methanation is expensive. Hydrogen production via water electrolysis demand substantial renewable energy, adding to the energy burden. Process optimization is complex, requiring careful balancing of the CO methane hydrogen cycle in large scale operation. Integrating the gas recycling system also necessitates significant engineering adjustments and infrastructure changes. Addressing these changes and challenges is key to scaling this technology effectively. Now, coming to a very informative slides on the global project overview. The course 50 project in Japan focuses on CO2 reduction in steelmaking. The hybrid project in Sweden pioneers hydrogen-based iron making. The ALCOS initiative in the European Union targets ultra-low carbon dioxide steel production, while the HI Cerna process in the Netherlands innovates with a smelting reduction technology. These efforts demonstrate worldwide interest in sustainable iron making, providing valuable lessons for our methanation approach. Now, coming to the understanding of chemistry behind methanation. So, this is an exothermic reaction releasing heat as one of that is we can specify 1 mole of carbon dioxide react with 4 mole of hydrogen to form 1 mole of methane and 2 mole of water. The reactants are CO2, a major blast furnace byproduct, and hydrogen, often sourced from renewable energy like water electrolysis. The products are CH4, usable as a fuel or reducing agent, and S2O, released as water. This reaction heat release is a key factor in its energy efficiency, which we will quantify next. And finally, let's calculate the energy balance. The amount of CO2 available for methanation is 200 meter cube per hour using stoichiometry of CO2 plus 4 hydrogen CH4 2S2O. We need 4 moles of hydrogen per mole of CO2. Converting 200 meter cube of CO2 to mole at STP gives approximately 8.95 moles, requiring about 0.07 meter cube of hydrogen. The reaction releases energy calculated as 8928 moles of CO2 per hour times minus 165 kilojoule per mole, yielding 1473198 kilojoule per hour. This energy can be recovered to support other steelmaking processes and underscoring the technology's efficiency. That conduct our technical overview. Thank you.